In this video, we're going to take a look at how we describe chemical reactions, both word equations, skeleton equations, and balanced chemical equations. So why are chemical equations important? They happen around us, inside of us, all the time. Every breath we take, we're taking in oxygen for our body to use for respiration, to get the energy we need to move around, to think, and do all those bodily functions. And around us, we have plants going through photosynthesis, which then allow them to make glucose, which then we're able to consume for food. So in a chemical reaction, you have one or more substances that react to form one or more new substances. Looking at water that is in ice form, melting to go to liquid water, then that is just a physical change because it's still H2O and we haven't made any new substance. That substance remains the same. But when we bake bread, taking all those ingredients and flour and sugar and eggs and butter and mixing them together, that's just a physical change. When you put it in the oven to bake it, adding that energy, that heat from the oven, allows that reaction to go through and change that dough into bread. So the first type of reaction we're going to look at is a word equation. It just describes what things are going on inside of our reaction. It lists out all the reactants to the left, separated from the products by a yield sign, or that arrow as you see there, and again the products on the right. So here we see the reaction of iron and oxygen forming rust. We have iron plus oxygen yielding iron 3 oxide. In a word equation, again, you list out all the reactants and just in words as far as what's going on, separated by plus signs, and then you have the yield sign separating them from the products, and then you list out your products. If we had multiple products, they'd be separated by plus signs also. In this case, we didn't. Iron 3 oxide was the only substance that was being formed. We then can take these word equations and change them to chemical equations. That falls into two different categories: skeleton equations and balanced chemical equations. But when we take a word equation to put into a chemical equation, you take those words that were there and you change them into the symbols and formulas representing the substances that were reacting and being produced. So a skeleton equation just gives you those symbols and formulas of our reaction without putting them into relative amounts. It doesn't tell you how much of each thing is going in and how much of each thing is being produced. It just tells you what the symbols and formulas are of those substances. And also within that chemical equation, it will show things such as a catalyst. A catalyst is a substance that you put into a chemical equation, but it's not a reactant or a product because it doesn't get used up. It gets spit back out as quickly as it gets used, but it allows the reaction to go faster because it lowers the activation energy needed for that reaction to happen. So here we see some of the common symbols that you'd see in a chemical equation. Again, some of which we've already seen: the plus sign and the yield sign. The plus sign separating both reactants and products from each other. Yield sign separates the reactants from the products. Sometimes reactions go both directions. It's what we call a reversible reaction or an equilibrium reaction. We have a double-headed arrow. Things that are solid, they get an S after them. Things that are liquid get an L. Things that are a gas get a G. And if it's dissolved in water, it gets an AQ for aqueous. If a reaction needs heat, like we talked about the baking of the bread, then we use the delta sign or just say heat above the yield sign. And if there's a catalyst used, that also goes above the yield sign, like we see here with platinum. So how do we get a skeleton equation? It's pretty simple. Just take a word equation, as we see here, and dissect it down and put it into the symbols and the formulas that are needed for those substances within this reaction. So we have solid iron 3 sulfide reacting with gaseous hydrogen chloride to make solid iron 3 chloride and dihydrogen monosulfide gas. So let's take it piece by piece and work our way through this equation here. So first off, we have solid iron 3 sulfide. Iron 3 sulfide is the ionic compound. Since iron is a metal, sulfur is a nonmetal, they make an ionic compound. Iron 3, since it's a transition metal, has that Roman numeral. That makes it a little bit easier. We already know its charge from the Roman numeral that's there. It's a +3. Sulfur in group 6 needs 2 more electrons. It makes a -2. When we crisscross those valences, we get iron 3 sulfide to be Fe2S3, again S for solid. It then says reacts with, so we know there's another reactant, so we add in a plus sign to now separate our reactants from each other. It reacts with gaseous hydrogen chloride, again ionic, hydrogen +1, chlorine -1, so HCl, gaseous, G for gas. To form, so now we put the yield side in because we know we're going to be forming or producing new substances. And that first substance which is going to be produced is solid iron 3 chloride. again an ionic compound, iron 3 plus 3 iron, with chlorine, which is in group 7, so it makes a -1 charge. We crisscross that and we get FeCl3, and again, since solid, it gets an S. And again, since there's another product being formed, we need the plus sign to separate them from each other. Dihydrogen monosulfide gas. Looking at its name, those prefixes tell us it must be molecular, and we can use those prefixes to now tell us the subscripts for that compound. So dihydrogen H2, monosulfide, just one S, doesn't need a subscript, so H2S. Again, it's a gas, G for gas. But lastly, the most common way in which you see equations is as a balanced chemical equation. It gives you those relative amounts of each thing that's being reacted and produced in a reaction, because we know that mass is always conserved. You cannot create nor destroy mass within science. So the number of atoms that are reacting have to equal the number of atoms that are being produced for each element that is involved. Whatever you begin with, you need to end with. So that way, every single atom is balanced and accounted for within that reaction. All atoms of every element in that reaction are balanced to each other as a reactant and as a product. You do this by changing the coefficients, because putting a coefficient in front isn't going to change anything about the substances that are there. It just changes how much of each thing is there. It's kind of like looking at a label on a package of Oreos. It lists out the ingredients that are in Oreos, and it does list them in terms of which one happens with the most amount through the one with the least amount, but you can't just take those ingredients and throw them together and make Oreo cookies. In a word equation, same idea. It lists out what reactants and products there are, but in a balanced chemical equation, actually be like having the recipe, because it gives you those relative amounts of each substance in that reaction. So in balancing equations, we can't ever change the subscript that's there, because when I change the subscript, it changes what that substance is. Earlier we had iron 3 chloride, but we also have iron 2 chloride. So if I change that subscript from a 2 to a 3, then that changes what that substance is, because it could actually be another substance, or change it to something that doesn't even really exist. Nor can you take a coefficient and stick it in the middle of a compound. You can't just split that compound in half and put a coefficient in the middle of it to then make it balance out. Even though it'd be easier to do, it wouldn't make any sense. It'd actually look really silly to have a coefficient in the middle of a formula. So some tips when you're trying to balance equations. The first one is, if it's in an elemental state, just leave it till the end. So that way, whatever coefficient you need to make it balance out doesn't affect other substances within that reaction. So if you save it for the very end, you can then just slap in that coefficient and make it all balance out. For polyatomic ions, they get a little bit tricky because you have parentheses. You distribute the subscript into the parentheses and follow that along as it goes. If it remains as one polyatomic ion from the reactant side to the product side, then just treat it all as one substance rather than try to break it up into its little components. If you start with the ones that have the larger subscripts first, sometimes that also makes it easier, because those are ones probably don't ever change, or certainly going to need a lower coefficient than everything else. So if you start the large ones first, it kind of makes the other ones fall into place a little bit easier. And also, if you follow along as you change your coefficients to then the other substances, the other elements that are in that substance, and how they now unbalance the other side of that reaction, and kind of work your way back and forth between the reactants and products, following along each one, rather than try and jump back and forth and just look at every element individually. If you kind of follow along like dominoes, as far as now this changed, what did it do to the other side, and bounce back and forth for each change you make, it kind of gives you an order. And then lastly, when you're all done, double check. Make sure that after you've added these coefficients in, you didn't accidentally change something that was balanced to now unbalanced. And also, make sure you're in the lowest whole number ratio, because as you add in new coefficients and follow it backwards, maybe try and double things, the next thing you know, you have coefficients of 4s and 8s and 12s, and you can divide them all down to something much more simple, 1s and 2s and 3s. So let's take a look at a few different equations and how this kind of works out. So we'll take our old skeleton equation, which we already made with our iron 3 sulfide, our hydrogen chloride gas, and our iron 3 chloride and dihydrogen monosulfide that is produced. Let's make this thing balance out. So a quick analysis of this reaction tells us there's 2 irons on the left, only 1 on the right, and 3 sulfurs on the left, and only 1 on the right, and 1 hydrogen on the left, and 2 on the right, and 1 chlorine on the left, and 3 on the right. So not one of those elements, not one of the atoms of those elements are balanced out. So this looks like it's going to be a lot of work, but if you kind of follow it along, it doesn't end up being too big of a mess. So we see those 2 irons on the left, 1 iron on the right. So if I put a 2 in front of my iron 3 chloride, Now it gives me 2 irons on the right because I have 2 iron 3 chlorides, each with 1 iron within them. So now it gives me 2 atoms of iron on the right. I had 2 in my 1 formula unit of iron 3 sulfide on the left. But now that gives me those 6 chlorines, and I only have 1 on the left. So now let's make those balance out. If I put a 6 in front of my HCl, now having 6 different HCls, each with 1 chlorine in them, that gives me those 6 chlorines to balance the 6 that I just made on the right. And that now gave me 6 hydrogens on the left. So now we'll jump back over the right side and find a hydrogen on the right side. And there are 2 in my dihydrogen monosulfide. So if I put a 3 coefficient in front of that, it gives me the 6 hydrogens that I need to make those 2 sides balance out. And lastly, that 3 in front of my H2S gives me 3 sulfurs. And luckily, yes, there are 3 sulfurs on the right side of the equation, and therefore we're all balanced out. All reactions that actually happen, they are able to be balanced out. If you went from a word equation to then try to get to a balanced equation and you just keep changing coefficients and it doesn't balance out, you probably made a mistake in one of the formulas of one of those substances within that reaction, if not multiple substances within that reaction. So next we'll take a look at one that involves a polyatomic ion. So here we have ammonium, NH4. So ammonium oxide, so I do need 2 ammoniums to balance out the 1 oxygen, and that's why we have those parentheses around our ammonium, but there's only 1 on the left. And again, we could treat it as just one thing as ammonium because it isn't changing, but for this purpose, let's just take a look at, let's pretend that it is changing and how that kind of all works together. We also have 1 aluminum on the left and 2 on the right, and 3 chlorines on the left and 1 on the right. So let's start off and fix our aluminums. So I have 2 aluminums on the right, I only had 1 on the left. Putting a 2 in front of my aluminum chloride on the left now gives me 2 aluminums on the left, but that also now changes my chlorines. So now I have 6 chlorines on the left. So let's fix those on the right. I'm putting a 6 coefficient in front of my ammonium chloride. Now it gives me 6 chlorines. It also now gave me 6 nitrogens and 24 hydrogens. So I need to make that balance on the right. So putting a 3 in front of the NH4,2O, again now I have 2 NH4s, which is really 2 nitrogens and 8 hydrogens times 3 each, makes that balance out because now I have 6 nitrogens and I have the 24 hydrogens, which I had on the right side. And lastly, I have 3 oxygens now, and then I do have 3 oxygens on the right side, so those balance out. However, again, I could have treated ammonium as one thing, and yes, I have 6 ammoniums on the left because I have 3 times the subscript of 2, so 6 ammoniums in total on the left, and I have 6 ammoniums on the right from that coefficient in front of it. And lastly, here's one where it kind of works out nicely, you'd think, because we have oxygen by itself, but it is diatomic oxygen, which is going to bring in a little wrinkle. But the other nice thing we notice about it, though, it is all by itself on the left side, and it's in 2 different substances on the right side. So if I was trying to balance with oxygens, it does get tricky. So it's a good thing that's all by itself, because it'll make it easier in the end. So let's balance off the carbons and the hydrogens first. I have 2 carbons on the left. I have only 1 on the right. So I'll put a 2 in front of my carbon dioxide, and that makes my carbons balance out. 2 carbons on the left, 2 on the right. Same thing with my hydrogens. I have 6 hydrogens on the left. I only have 2 on the right. So if I put a 3 coefficient in front of my water over there on my right, now it gives me those 6 hydrogens, which now balances out. Let's tackle that ugly thing of oxygen there. I have 4 oxygens coming from carbon dioxide. I have 3 coming from water. So 4 plus 3, I have 7 oxygens in total on my product side. I have 2 on my reactant side. I could put a 3.5 coefficient in front of that oxygen, and it does make it balance out, and all is good if we are on the macroscopic scale. If I'm looking at this in terms of moles, 1 mole of C2H6 and 3.5 moles of O2 makes 2 moles of carbon dioxide and 3 moles of water. That works out okay. But on a microscopic scale, now you're looking at molecules of each of these. You can't have 3.5 molecules of oxygen, so that doesn't make any sense. However, I do know it is balanced, so now I just make that half go away. And what can I do to make a half go away? If I double every single substance, every coefficient of each substance within this reaction, it will then make everything else balance out and we'll still be in good shape. So changing the 1 coefficient that was understood to be in front of C2H6 to a 2, and the 3.5 to a 7, and the 2 to a 4, and the 3 to a 6, now I know it will still balance out. And a quick check, 4 carbons in, 4 carbons coming out. 12 hydrogens going in, 12 hydrogens coming out. 14 oxygens going in, and 14 oxygens coming out. Everything still balances after I've doubled up all its coefficients, because by doubling all of them, I change them all by a 2 factor. It still remains balanced.